This video is going to go over the concept of one sample match pairs scenario, one sample match pairs inference. So first thing we're going to review is what is match pairs. Remember back to the experimental design unit, there was a special type of blocking, and the special type of blocking was called match pairs. Remember, there's a few different types of match pair scenario. Match pairs, notice, has the word pairs. So hopefully you're realizing that pairs means two. So remember, that's blocks of size 2. And basically what we were doing was we were grouping people together who have something very similar with respect to what we were measuring, some kind of confounding variable that we want to reduce. So we block or we pair based on the similarity that they have in common to try to reduce the effect of that lurking or confounding variable. So a few different types of match pairs that we did. One was self-self. And the self-self that we talked about were before and after. So you might implement some kind of treatment on someone, and you might measure them before and after the treatment and compare themselves to themselves and see if they improve. Another type was if they have 2 limbs and you want to give one treatment to one limb and one to the other, and you compare themselves to themselves, like the question where we put the sunscreen on the one arm and then the other sunscreen on the other arm, and then they compare themselves to themselves. The other type of match pairs is actually a block of size 2, where you're pairing people who are as alike as possible with respect to that variable. So the actual pairs that we talked about could be twins, could be married couples, could be things like that. Okay, so maybe we're just separating people based on their gender and their height. We just block them in terms of size 2. And then remember, what we do is we flip a coin and we let heads represent the one person gets the one treatment, tails be the other, and then you compare within the pair. All right. So now we're going to actually talk about how we can analyze this data with respect to inference. So here is the example. We have twins, okay? And it turns out these twins were separated at birth. So they are identical twins. So they should be pretty alike, right? And since they separated them at birth, they went to 2 different families. The one twin, twin A, went to the high income family, and the other twin, twin B, went to the low income family. And then they were given an IQ test as adults, and they compared the twins to each other. So this is an example of pairs, in this case twins, who should be as similar as possible with respect to their genetics. So if we were to compare their IQs to each other, you would think that at least they're very similar because they have the same genetics, okay? And then the thing that we're measuring is their IQ, and we're thinking that maybe the high income or the low income background could play a role. So basically what you see is these numbers 1 through 12 represent the pairs of twins. And each one is separated into twin A or twin B, high income, low income, high income, low income. So if we were to plot them separately, you see on this first dot plot, we have just twin A and the next one twin B, and you could describe that there could be some similarities or differences within the dot plots. They both seem like the shapes are skewed to the right. It does look like this twin A high income family may have a higher median and a higher mean than IQ than the low income family, but is it statistically significant enough of a difference? Okay, so the center of twin A looks to be greater than twin B. The high income twin looks like they might have a higher median and a higher mean than twin B, but is it statistically significantly enough of a difference? So rather than find the mean separately, which we could do, we can find the difference of each pair, and then we can just analyze them as a one sample situation. So basically what they do is they look at the pairs, and instead of doing the mean of A, the standard deviation of A, the mean of B, the standard deviation of B, they find the difference between each pair, and it looks like they did A minus B here, and it's important to determine the direction of which way you're subtracting every time and be consistent here. So they did 128 minus 120, and they got 8. Then they did 104 minus 99, and they got 5, etc. And notice if you look at this last row, I'm going to highlight it in yellow, this is the difference column. Okay, and if the difference, let's write this down, if the difference is positive, that means that twin A had a higher IQ than twin B, because 128 minus 120 is positive 8. Twin A scored 8 points greater than twin B, 104, etc. So if you have a negative difference like this one, this is the one where twin B actually did greater than twin A by 1 point, but most of them look like they're positive, meaning twin A did better than twin B. So now what we can do is, instead of separately finding the mean and the standard deviation of twin A and twin B, we can find the difference column, or difference row in this case, and we can just find the one mean. And the one mean that we find, because it's a sample, is going to be called X bar D. And that stands for the mean of the differences between the two groups. And we can also find the standard deviation S sub D, standard deviation of the differences. So I'm going to show you what I did, okay? Instead of L1, actually, I'll show you, I'm going to do it in L3. I went to Stat Edit, and I entered twin A in L1 and twin B in L2. And they already found the differences for us on this paper, but I want to show you what I could have done. I could have highlighted L3, and I could have done L1 minus L2, which is second 1 minus second 2 for L1 minus L2. And when I hit enter, it populates list 3 with all the differences which you see here, 8, 5, 9, etc. Okay, so now what I'm going to do is I'm only going to find the mean of the difference column, which for me is L3. But you guys could have just put in all this data into L1 for 8, 5, 9, 6, and you could have just found the mean of the differences right away. So to do that, I'm going to go to Stat, go over to Calc, choose number 1 var stat, and I'm going to do L3, which is second 3, and I'm going to hit Calculate. Now I get a mean of 5.833, which is X bar of the differences. So notice this is a positive mean, indicating that the mean of the differences is showing that twin A did better than twin B, and also the standard deviation S is 3.927. Okay, so now I'm only going to look at the plot of the differences. Okay, so I have a sample of size 12, so I can't use the central limit theorem. Okay, so I have to plot the data, and I have to look at the plot to make sure there's no extreme outliers or skewness before I proceed. So I'm going to go to second y equals, hit enter on plot 1, hit enter on the word on. I'll choose this one, and I'm going to do second 3, L3. I'm going to make sure there's nothing in Y1 and zoom 9. So this looks pretty good. So this is approximately symmetric with no extreme outliers or skewness. Nice. Okay, so it says describe the shape. So I want to say my plot shows approximate normality or symmetry with no extreme outliers or skewness. So I am allowed to proceed with T procedures. So I just wrote that down. We can't use the central limit theorem. We plot the data because it's approximately normal with no extreme outliers or skewness. I can proceed with T procedures, and I labeled this plot the differences of the IQs twin A minus twin B. So here you could see that I specified the difference is twin A minus twin B, and often you're going to see the subscript, the letter D for difference, like this, lowercase d italicized, or you're going to see the word DIFF for difference. So notice here that it says it depends on if we're going to do a 1 sample or 2 sample problem, depending on how the data were selected. So it is important to note if you're talking about each individual and you're doing something where it's like a before and after situation, and that's actually 1 sample of people who you're comparing themselves to themselves, or you have the pairs of similar individuals like the twins, that's also a matched pair setting. So that is different than the two sample setting where you have two independent samples and you're separately measuring the mean of one, the mean of the other. So we have to be careful that it's either a one sample problem or a two sample problem. Now, a quick reminder before we proceed that the one sample procedure, one sample means, has the following rules or conditions that we have to check. They're the same ones as always, the SRS. We have to do 10n is less than the population of interest, and we have to check that the sampling distribution is approximately normal. We could use the CLT, or if it's not met, we plot the data and we look at the plot of the differences. So that's important to note, the plot of the differences. Notice here we have that subscript DIFF for differences. So we're just going to continue the example above. It says construct a 95% confidence interval for the mean difference of IQs. So the mean difference means mu subscript difference, okay? Or we could write mu A minus B here, and that is the direction of the difference. So we would do panic. So remember, panic starts with a P. So it's going to be population of interest, parameter of interest, etc. So let's just quickly go over these bullet points. The population of interest would be all pairs of twins, of identical twins, separated at birth. And actually, it could be really all pairs of identical twins overall. We just happen to look at the ones that were separated at birth. The parameter is mu sub diff, and that's the mean IQ, the mean of the differences of the IQs of twins, of identical twins, of high income minus low income. Okay, so maybe the population is just all identical twins in general. They don't have to be separated at birth. All right. Now assumptions. First one, is it an SRS? Second one, is 10n less than the population of interest? And third one, plot the data. Okay, I would do all three. I'm going to pause the video here and actually go do them. So I did look back at my population, and it did say that it was stated to be twins taken from those who have been separated at birth, a random sample of identical twins who have been taken from twins who have been separated at birth. So it is, the population of interest is all twins who have been separated at birth, all identical twins who have been separated at birth. Okay. And then we have over here, it said it was an SRS because they said that it was a random sample, so that's met. 10 times 12 is 120. Is that less than all pairs of twins separated at birth? I would hope not, but maybe that's kind of sad. And then we plot the data and we see that the sampling distribution, we see that the plot of the differences is approximately normal with no extreme outliers or skewness. So the x-axis here would be differences of IQs. A minus B. All right. So now we're allowed to proceed with the name. So the name is going to be A. It's actually only one sample, even though you guys think it's probably two samples, because we found the difference of the two. It's actually one sample because we're only analyzing this difference row. Okay. Since we're only analyzing this difference row, this is actually only one sample of size 12. So this is one sample, this is means. So is it going to be a Z or T? I'm hoping you're going to say it's a T, and it's going to be an interval. One sample T interval, matched pairs, all right? So we're done with that. And now you guys know the formula for an interval, for a one sample T interval. Remember, statistic plus or minus critical value times standard error of the statistic. So it's going to be X bar for the statistic of the differences, plus or minus, and then is it Z or T? I'm hoping you're saying it's T star times the standard error of the mean. You guys know standard error of the mean is S over radical N. So it's going to be S of the differences over radical N of the differences. All right. So remember, our differences were located in stat edit L3 for me. So if I had run stat calc 1 var stat L3, I would have had the x bar of the differences and the s of the differences. So I'm going to put in 5.8333 plus or minus t star. I'm going to have to look it up, and I can. And s is 3.927 over radical 12. So you guys remember, we can look up t star if it's an easy degrees of freedom. So there was, n was 12. 12 minus 1 is 11. So we actually can look up the t star for 11 for 95%. So look it up now. Let's pause the video and let's look it up now. So here is the t star for DF11. Remember, DF is n minus 1. 12 minus 1 is 11. 95%, we get 2.201. So let's plug that in here for t star, 2.201. Now remember, we are not actually going to do this by hand. Now we're going to the calculator to get our interval. So we're going to press that. We're going to go over to test. We're going to choose t interval, which is number 8, and it's only one sample, t interval. If you have data in your list, you could choose data. My data was in L3, so I'm going to press second 3 because that's where the differences lie, and 95%. So I have my interval, and it is all predominantly positive numbers. So we have 3.338. 2, 8.3, 2, 8.7. Okay, so my last step is conclusion and context. So remember my sentence for my interval. It is, I am blank % confident. The true blank is between blank and blank. I am 95% confident. The true mean of the differences of IQs between twin A and twin B, between, we shouldn't say twin A and twin B because those were the samples, between, let's say, high income raised twins minus low income raised twins is between 3.338 points and 8.3287 points. So this begs the question, if it had been a null hypothesis of the mu diff equals 0, and this were the interval from 3.338 to 8.3287, and this were the 95% level, would we have rejected our null? Think about, oh, 0. Where is it located? It's to the left. So it's in the tail. So will we reject the null? I'm hoping you would say yes. P is low because it's in the tail. Reject the null. And then you would rule in favor of HA, that there is indeed a difference between the two. And that means probably that the IQ of the high income twin actually was indeed greater than the low income twin. So this is statistically significant enough information. So I just want to remind you, if your whole interval is all positive numbers, that this confirms that there is statistically significant evidence that twin A's IQ was greater than twin B's IQ.